Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This is the 48th video that I am making based on individual articles in the book, and it is the first video in a playlist on samples. There will be two more, sample size part 1 and sample size part 2. Also, I had earlier completed a video on the topic of sampling distribution. This is in the playlist for distributions because it doesn't have much to do with the concept of sampling as we're addressing it here. If you want to know the latest status of the videos I have been working on and what's next, please see the videos page on my website, statisticsfromatoz.com/videos. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This will end with the highlights of the concept on a single page. And then we'll go into detailed explanations of each of the keys. For this video, there are 6 KTUs. The first key to understanding tells us that to get a good sample which accurately represents the population or process from which the sample was collected, we need to minimize sampling error and sampling bias. Sampling error can generally be decreased by increasing sample size. The second KTU says sampling bias causes a sample to not be representative of the population or process. Slide number 4. The second KTU says sampling bias causes a sample not to be representative of the population or process. Key number 3 says, if possible, obtain a sampling frame which includes all members of the population or process. Key to understanding number 4 says randomness is likely to be representative. Simple random sampling, SRS, can be the most effective method of achieving randomness. The fifth key to understanding says other sampling methods include stratified sampling, clustered sampling, and systematic sampling. The sixth and final key to understanding says statistical process control uses a special type of sample, the rational subgroup, to block the effects of potential causes of variation. And here on one page are the 6 keys to understanding the concept of samples and sampling. You may wish to pause the video at this point and read them all together. Okay, now let's take a closer look at each key to understanding. Key number 1 tells us that there are 2 things we should try to avoid. It says to get a good sample which accurately represents the population or process from which it was collected, we need to minimize sampling error and sampling bias. Let's start with sampling error. We'll deal with sampling bias in KTU number 2. KTU number 1 goes on to say, sampling error can generally be decreased by using a bigger sample size. Most often we don't have all the data from the entire universe under consideration, so we collect a sample of data. Then we calculate a statistics, for example, the mean from the sample data. There is a calculatable probability that our particular sample is not a good representative of the population or process. We know, for example, that flipping a coin should result in 50% heads and 50% tails. If, however, we flip the coin only 4 times, we could easily get a very different result, as shown in this illustration. If you only flip a coin 4 times, your result is more likely to not have an even number of heads or tails than it would have with a much larger sample size. This is called the sampling error. It is not an error in the sense that a mistake has been made, but because even some large samples may vary significantly from the true statistic. The point is that in larger samples, the chance of a sampling error is smaller. So how do we minimize sampling error? By having a sufficiently large sample size. And that subject will be addressed in my 2 videos on sample size. In addition to sampling error, sampling bias is the other thing we need to avoid or minimize. Key number 2 says sampling bias causes a sample to not be representative of the population or process. And sampling bias is further divided into 2 different types, selection bias and response bias. Let's start with selection bias. Here's an example. Let's say we are polling potential voters prior to an election, and we decide to collect data only from people who are entering or leaving a particular women's clothing store in a shopping mall from 6 to 9 p.m. Now, there are a whole lot of reasons why this data is not likely to be a good representation of the population at large. First, more women than men will be going in and out of a woman's clothing store. And secondly, people who work the evening shift will be excluded if we poll only from 6 to 9 p.m. They'll still be at work. And people who are not eligible to vote can be included. And if the mall caters to either high-income or low-income customers, the other income levels will be underrepresented. And if the mall is in a city center, then rural and suburban voters will be underrepresented, or vice versa. Now, selection bias can also occur in sampling other than for polls and surveys. For example, in manufacturing, inspectors of physical items tend to select for their sample those items which have a visible defect. Another type of bias is response bias. Almost all polls and surveys suffer from response bias. Many people will not take the time to respond to questions. People with more time on their hands are more likely to respond. This can lead to overrepresentation of retired people and the unemployed, and people who don't have 2 screaming toddlers clinging to them. People with strong opinions about the question are more likely to respond, and patient people are more likely to respond than impatient people. Okay, that's it for sampling bias. Now we have key to understanding number 3, which says, if possible, obtain a sampling frame, which includes all members of the population or process. A sampling frame is a list which identifies all possible units that can be selected for our sample. An example would be a list of registered voters or a numbered list which uniquely identifies each item produced in a manufacturing run. A sampling frame can be used in the sampling methods described in the slides that follow. KTU number 4 says, randomness is likely to be representative. Simple random sampling, SRS, can be the most effective method of achieving randomness. There is no bias in true randomness. In a random selection method, each possible sample of a given sample size is equally likely to be selected. So a random selection method is unbiased. So if the sample size is large enough to reduce the sampling error to a tolerable level, and for more on this, see the articles on sample size and the videos, the sample will be as representative as possible. To implement simple random sampling, a randomizing technique is needed. This can take the form of picking numbers out of a hat or using a computer random number generator, such as that provided by most spreadsheet software. With a random number generator, the list of units in the sampling frame is numbered, and the units corresponding to the generated numbers become the sample. KTU number 5 says, other sampling methods include stratified, clustered, and systematic. Let's start with the stratified method. Step 1. In stratified sampling, we divide the population or process into homogeneous subgroups whose members all share a common characteristic. Such homogeneous subgroups are called strata, which is how this method gets its name. For example, we could divide a population into two strata, female and male. Everyone within either of these homogeneous groups is the same gender. Step 2, we select a simple random sample from each stratum. The sample size for each stratum corresponds to a known proportion of the stratum in the population or process. In this case, roughly 50% for both male and female. The advantage to this approach is that it avoids selecting a sample which we know is not representative, and the disadvantage is that it can't be used when there are no homogeneous subgroups. The second of the three sampling methods we will discuss is called clustered sampling. Step 1, we divide the population or process into small clusters. A cluster, for example, could be all the voters living in a single city block. Then we select a simple random sample of these clusters, say 30 city blocks. Then we collect data from each unit within each cluster within that sample. For example, we go door to door and try to survey someone from every residence in each of the clusters, that is, each of the city blocks. The advantage is that we save time and money. In a given amount of time, a pollster can poll a lot more people walking door to door on a block instead of polling people widely spread across multiple city blocks. Also, one does not need a sampling frame listing all the individuals, just a list of all clusters. The disadvantage is that the increased variability due to differences between the clusters may reduce accuracy. The third and last method we'll cover is systematic sampling. To use this method, we need a sampling frame, which again is a complete list of all the items from which a sample will be taken. And here's the four-step process for performing systematic sampling. Step 1, number the items in the sampling frame from 1 to n. Step 2, randomly select or generate a number j to be the first unit selected for the sample. Don't just start with 1 because that would not be random. Step 3, select the kth item after that to be the second item selected. More on this in the next slide. And step 4, repeat until the desired sample size n is reached. You may wish to pause the video at this point to read those 4 steps again. To continue about systematic sampling, k is a number which tells us how many items to skip when picking the next item from the sampling frame. K can be randomly selected, but it must be small enough to yield the desired sample size n. Here's a method for making sure it is small enough. If capital N is the total number of items in population or process, and if j is the random number generated for the first item to be selected, then k equals the quantity n minus j divided by small n, the sample size. Round down to an integer. The advantage of systematic sampling is that if the sampling frame is ordered in some obvious or non-obvious manner, systematic sampling avoids a sample comprised of a disproportionate number of units from the top or the bottom of the range. Its disadvantage is if the sampling frame has periodic variations which coincide with k, the sample will not be representative. Up to this point in the video, the sampling has been for use in inferential statistics. Examples of inferential statistics are t-tests, ANOVA, and regression. And the data universe from which samples are drawn has been a population. Now there's a discipline called statistical process control, SPC, which is used with ongoing processes instead of populations. For example, a manufacturing process is constantly producing new items from which samples can be collected for inspection. The Six Sigma process improvement methods use statistical process control, SPC. And control charts are a common tool in SPC, and it's used to assess and improve consistency. We need a special kind of sampling method to determine whether a process is under control or not. These are covered in the book in articles on control charts. To this point, I have not yet done videos on those articles. In statistical process control, We collect a number of small samples in order to identify variation over time. These are a special kind of sample called the rational subgroup. The rational subgroup samples could be as small as, say, n equals 4 or 5 items, and we collect 25 more of these subgroups of 4 or 5. And rational subgroups are comprised of individual data points collected from a process under the same conditions. For example, they will be collected at the same operation, or under the same operator, or within a narrow time frame. These conditions are kept the same because we want to eliminate, that is, to block them as potential causes of variation. We can calculate a statistics, for example, the mean, or the proportion, standard deviation, or range for each rational subgroup. It is the values of that statistic for each rational subgroup which gets plotted in the control chart. Okay, that completes this video, which is the first in a small playlist of 3. And see my website for statisticsfromaz.com/videos for the latest status of videos completed and planned. If you liked this video, please remember to press the thumbs up like button on your screen below. And I'll be making more videos of some or most of the 60+ concepts in the book. If folks like you tell me more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromaz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip series, as well as posts showing that you are not alone if you are confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z and on Twitter as @StatsA to Z.